why the universe remembers everything. Let me tell you something that will change the way you think about every single thing you've ever done, every word you've spoken, every step you've taken. Every breath, every mistake, the universe recorded all of it, not metaphorically, not poetically, physically. The universe remembers everything, and nothing, absolutely nothing, can ever be erased. I'm Leonard Susskind. I've spent over 50 years working on the deepest problems in physics. Black holes, quantum mechanics, the nature of information itself. And what I've learned, what decades of theoretical breakthroughs and bitter scientific debates have confirmed, is something most people have never heard. Information cannot be destroyed, not by fire, not by time, not by death, not even by a black hole. This is not philosophy. This is one of the most fundamental laws of nature, and its implications are staggering. Let me start with something simple. You burn a book, the pages curl, blacken, turn to ash and smoke. The words are gone. The story is destroyed. Right? Wrong. Every single piece of information in that book still exists. It's been scrambled, yes, scattered into trillions of particles of smoke and ash and infrared radiation, but it's all still there. In principle, if you could track every single molecule of smoke, every photon of heat radiation, every ash particle, and if you could reverse their motions perfectly, you could reconstruct the book. Every word, every page, every ink molecule back in its original position. This isn't magic. This is what the laws of physics demand. The fundamental equations of physics, whether you're talking about quantum mechanics or classical mechanics, are reversible. They work the same way forward and backward in time. If you know the complete state of a system at any moment, you can calculate its state at any other moment. Past or future, information is never lost in the equations. It's just redistributed. Think about that for a moment. Every conversation you've ever had sent sound waves into the air. Those sound waves bounced off walls, dissipated into heat, were absorbed by objects around you. But the information in those sound waves didn't vanish. It was converted into tiny temperature fluctuations, molecular vibrations, subtle rearrangements of matter. Your words are still out there. Encoded in the thermal noise of the universe, unreadable to any practical technology, yes, but physically present, still real. Now, you might think this is just a theoretical curiosity, and say, fun thought experiment with no real significance. But this principle, the conservation of information, turned out to be at the center of the most important debate in the history of theoretical physics, a war that lasted 30 years. It's a war between me and Stephen Hawking, and it changed everything we understand about the nature of reality. Let me take you back to 1974. Stephen Hawking, who was already one of the most brilliant physicists alive, made an extraordinary discovery. He showed that black holes aren't completely black. They emit radiation. It's faint thermal radiation, now called Hawking radiation, leaking slowly from the event horizon. This was stunning. Nobody expected it. It's a black hole, the ultimate cosmic prison from which nothing can escape, was actually glowing, faintly, incredibly faintly, but glowing nonetheless. And here was the really disturbing part. Hawking's calculation showed that this radiation was perfectly thermal, random, featureless. It contained no information about what had fallen into the black hole. Think about what that means. You throw a book into a black hole. The book crosses the event horizon and is gone. Over billions of years, the black hole slowly evaporates through Hawking radiation. Eventually, the black hole disappears completely. All that's left is a cloud of thermal radiation, but that radiation is random. It doesn't encode the contents of the book. The information in the book is just gone, destroyed. This was the black hole information paradox, and it was a crisis. Because if information can be destroyed by a black hole, then the fundamental laws of physics are wrong. Quantum mechanics, the most successful theory in the history of science, requires that information is conserved. It's built into the mathematical structure of the theory, a principle called unitarity. Unitarity means that the quantum mechanical evolution of any system is reversible. You can always, in principle, reconstruct the past from the present. If black holes destroy information, unitarity is violated, quantum mechanics is broken. Hawking was comfortable with this. He argued that black holes really do destroy information, that quantum mechanics needs to be modified near black holes, that the rules change when gravity becomes extreme. I was not comfortable with this, not at all. And neither was my colleague Gerard T. Hooft, the Nobel laureate. We believe that information must be conserved, that quantum mechanics is exact, hence, that there had to be something wrong with Hawking's calculation, not with the fundamental laws of physics. This was the beginning of the black hole war. It lasted from the mid-1970s to 2004. Hence, 3 decades of arguments, calculations, thought experiments, and intellectual combat. Hawking on one side saying information is destroyed, me and T. Hooft on the other side saying it can't be. Hence. And the stakes were enormous. This wasn't about some obscure technical detail. This was about whether the laws of physics are consistent, whether the universe makes sense at the deepest level. Hence, whether reality itself has a coherent mathematical description. Let me tell you how we won, because we did win. And the way we won reveals something profound about the nature of reality. Hence, in the early 1990s, I started thinking about what happens to information that falls into a black hole. Where does it go? It crosses the event horizon. Hence, from the perspective of someone falling in, nothing special happens at the horizon. You just fall through. But from the perspective of someone watching from outside, something very strange happens. Hence, the falling object never actually crosses the horizon. It appears to slow down, redshift, and smear across the surface of the horizon. Hence, from the outside, it looks like the information is being stored on the surface of the black hole, not inside, on the surface. This was bizarre. And see, 3-dimensional object falls into the black hole, but its information ends up encoded on a 2-dimensional surface. It's as if the black hole is a hologram. Hence, the 3-dimensional interior is somehow equivalent to the 2-dimensional boundary. This idea, which I developed along with Tooft and later with others, became known as the holographic principle. Hence, it says that all the information contained in a volume of space can be described by a theory that lives on the boundary of that space. The interior is redundant. Hence, everything that happens inside is encoded on the surface. The holographic principle was radical, crazy sounding, but it had a precise mathematical realization. Hence, in 1997, the physicist Juan Maldacena, building on ideas from string theory, proved something remarkable. Hence, he showed that a specific theory of gravity in a 5-dimensional space is exactly equivalent to a quantum field theory, a theory without gravity living on the 4-dimensional boundary. Hence, this was the ADS-CFT correspondence, and it was a game changer because the boundary theory is a perfectly ordinary quantum theory. It obeys unitarity. Information is conserved. Hence, and since the boundary theory is exactly equivalent to the gravitational theory in the interior, information must be conserved in the gravitational theory too. Black holes can't destroy information. Hence, the information comes out in a Hawking radiation. It's incredibly scrambled, encrypted beyond any practical ability to decode, but it's there. The universe keeps a perfect record. Hence, in 2004, after years of mounting evidence Hawking conceded, he gave a famous lecture in Dublin where he admitted he was wrong. Information is not destroyed by black holes. Quantum mechanics is exact. Hence, unitarity holds. The universe remembers. Let me tell you why this matters far beyond black holes. Because the conservation of information isn't just a rule about black holes. Hence, it's a fundamental law of nature. It applies everywhere, to everything, to you. Here's what I mean. Your body right now is a specific arrangement of roughly 7 octillion atoms. Hence, that arrangement encodes information. An enormous amount of information, the structure of your DNA, the connections in your brain, the pattern of your fingerprints. Hence, the specific configuration of every cell, every protein, every molecule, all of it is information. And the laws of physics say that information cannot be destroyed. When you die, your body decomposes. Hence, atoms scatter, molecules break apart. But the information, the complete quantum mechanical description of every particle that was you doesn't vanish. It disperses, and it gets scrambled into the environment. It becomes part of the soil, the air, the water, the radiation field, but it's still there. And in principle, with a godlike ability to track every particle, you could reconstruct the complete quantum state of a person who lived 1,000 years ago. The information still exists. And it's just been redistributed across the universe. Now, I need to be careful here because I don't want you to misunderstand what I'm saying. I'm not saying we can actually recover this information. Hence, we can't. The scrambling is so thorough, so complex, so entangled with the rest of the universe that no conceivable technology could ever decode it. Hence, this is a matter of practical impossibility, not fundamental impossibility. The distinction matters enormously. Practically impossible means we'll never do it. Hence, fundamentally impossible means the laws of physics forbid it. Information destruction is fundamentally impossible. Information recovery is practically impossible. The universe remembers, hence, we just can't read its memory. But here's where it gets really interesting, because the conservation of information has implications that go far beyond individual books or bodies or black holes. Hence, it tells us something deep about the structure of reality itself. Think about the entire universe. Hence, every event that has ever happened, every star that has formed and exploded, every galaxy that has collided, every photon that has been emitted and absorbed, every quantum interaction between every particle since the Big Bang, all of that information still exists. The universe is its own perfect record. Nothing has been lost. Nothing can be lost. The Big Bang was a specific initial state. Hence, call it the initial quantum state of the universe. From that state, the universe has evolved according to the laws of physics, unitarily, reversibly. Hence, the current state of the universe encodes the complete history of the universe. Everything that has ever happened is written in the current arrangement of matter, energy, and fields. Hence, you just need to know how to read it. The light from distant galaxies carries information about events billions of years ago. Hence, the cosmic microwave background radiation carries information about the universe when it was only 380,000 years old. Hence, gravitational waves carry information about black hole mergers that happened in distant galaxies. Neutrinos streaming through space carry information about the nuclear reactions in the cores of stars. Hence, the universe is drenched in information, saturated with it. Every cubic centimeter of space is a library. Every photon is a messenger. Every particle carries a piece of the cosmic record. And none of it is ever destroyed. Let me push this even further, because the conservation of information connects to something I've thought about a great deal. Hence, the holographic principle I mentioned earlier, remember, the holographic principle says that all the information in a volume of space can be encoded on its boundary. Hence, the maximum amount of information that can be contained in a region of space is proportional not to the volume, but to the surface area of the boundary. Hence, this was first suggested by Jacob Bekenstein, who showed that the entropy of a black hole is proportional to the area of its event horizon, not the volume, the area. This is deeply counterintuitive. Hence, you'd think a bigger volume could hold more information. But no, the maximum information content is determined by the surface area, and the numbers are staggering. Hence, the maximum information that can be stored on a surface is about 10 to the 66 bits per square centimeter. That's a 1 followed by 66 zeros per square centimeter. Hence, so a sphere the size of the observable universe, about 93 billion light years across, has a surface area that can encode roughly 10 to the 124th bits of information. Hence, that's the maximum information content of our observable universe, and the current state of the universe encodes everything, every event, every interaction. Hence, every quantum fluctuation since the beginning. The universe doesn't just remember everything in a very precise sense. The universe is its memory. The physical state of the universe is the record. Hence, there's no separate recording device. The universe itself, the arrangement of all its particles and fields, is the complete and perfect history of everything that has ever happened. Hence, now let me address something that I know is on your mind. What about quantum mechanics? What about the uncertainty principle? Doesn't quantum mechanics introduce genuine randomness? Hence, doesn't the collapse of the wave function destroy information? This is a subtle point, and it deserves a careful answer. Hence, in quantum mechanics, when you measure a system, the wave function appears to collapse. A particle that was in a superposition of many states suddenly has a definite state. Hence, the other possibilities seem to vanish. This looks like information destruction. Before the measurement, the wave function contained information about all the possible states and their probabilities. Hence, after the measurement, only one state remains. But here's the crucial insight. The wave function doesn't actually collapse. Not fundamentally, what happens is decoherence. Hence, the quantum system becomes entangled with the measuring device, which becomes entangled with the environment, which becomes entangled with the rest of the universe. Hence, the information about the superposition isn't destroyed. It's spread out into the environment. It becomes entangled with so many degrees of freedom that it's practically impossible to recover. Hence, but it's still there. In the many worlds interpretation, which many of us take seriously, all outcomes of every quantum measurement actually occur. The wave function never collapses. It just branches. Hence, every branch carries complete information. Nothing is ever lost. Even in interpretations where collapse is real, the information problem is more subtle than it first appears. Hence, the outcomes of quantum measurements are random. Yes, but the randomness itself is constrained by the laws of physics. The probabilities are determined by the wave function. And the wave function evolves unitarily. The apparent destruction of information and measurement is an artifact of looking at only one part of a larger entangled system. And zoom out to include the entire universe, and information is perfectly conserved. This is what I fought Hawking over. This is what 30 years of theoretical work confirmed. Unitarity is exact, and information is conserved. The universe keeps a perfect record. Let me tell you about something that makes this even more remarkable: quantum entanglement. Hence, when two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance. Hence, but what entanglement really is, at its core, is shared information. Two entangled particles share quantum information that can't be attributed to either particle individually. Hence, it exists in the correlation between them, in the relationship. And here's the beautiful part: as systems interact and become entangled, information doesn't disappear, it becomes distributed. Hence, shared among many particles, woven into the fabric of quantum correlations that connect everything in the universe. Hence, your body right now is entangled with the air you've breathed, the food you've eaten, the light that's bounced off your skin, the ground you've walked on. Hence, information about you is spread across an unimaginable web of quantum correlations. And all of it is conserved, all of it persists. Hence, the universe is not a system that processes information and throws some away. It's a system that processes information and keeps all of it. Forever. Every quantum interaction adds to the record. Hence, nothing is subtracted. Now, I want to bring this back to something personal, because the physics of information has implications that touch the deepest questions about existence. Consider this. Hence, every person who has ever lived left an indelible mark on the quantum state of the universe. Every breath they took changed the distribution of molecules in the atmosphere. Hence, every step they took changed the configuration of the ground beneath their feet. Every word they spoke sent sound waves into the air that eventually thermalized but never truly vanished. Hence, every photon of light that bounced off their face carried information about them out into space, traveling at the speed of light, spreading through the cosmos. Hence, right now, at this very moment, there are photons that bounced off the face of Julius Caesar traveling through interstellar space. Those photons carry information about Caesar's face. And it's incredibly faint, hopelessly scrambled, practically unrecoverable, but physically real, still existing, still propagating through the universe 2,000 years later. The universe remembers Caesar. It remembers everyone, it remembers everything, and it always will, because information conservation isn't something that fades with time. It's exact, it's permanent. It's built into the fundamental laws. A billion years from now, the information about this moment, about you sitting here absorbing these ideas, will still exist. It's redistributed, scrambled beyond recognition, entangled with the rest of the universe, but present, encoded in the quantum state of reality. There's something both humbling and magnificent about this. Every action you take, no matter how small, permanently alters the quantum state of the universe. You can't take it back, you can't erase it. The universe records every moment with perfect fidelity. Hence, there's a thermodynamic aspect to this that I should mention, because it connects to something fundamental about time. The second law of thermodynamics says entropy increases. Hence, things become more disordered, information becomes harder to access, harder to read, harder to decode. This is why you can't actually reconstruct the burned book. Not because the information is gone, but because it's been scrambled into a state of high entropy. The scrambling is irreversible in practice. Hence, entropy is what stands between the theoretical conservation of information and the practical recovery of information. Hence, the universe remembers everything, but entropy ensures that most of those memories are encrypted beyond any possibility of decoding. It's like a perfect diary written in an unbreakable code. Hence, every entry is there, nothing is missing, but you can't read it. You know, the information exists. You can prove mathematically that it must exist, but you can't access it. Hence, this is the deep connection between information, entropy, and the arrow of time. Time moves forward because entropy increases. Hence, entropy increases because information gets scrambled into more and more complex correlations, but the total information never decreases. Hence, the universe gets messier, more complex, more entangled, but never less informed. The arrow of time is not about information loss. It's about information encryption. The past isn't forgotten. It's encoded, hidden, locked away in correlations so complex that no finite being could ever decode them. But the laws of physics hold the key. The fundamental equations know the past perfectly. Hence, the universe has never forgotten a single thing. Let me tell you one more thing that I find profoundly beautiful about all of this. The connection between information and reality itself. And so over the past few decades, a growing number of physicists have come to believe that information isn't just something that exists within the physical universe. And information might be what the universe is made of. John Archibald Wheeler, one of the great physicists of the 20th century, coined the phrase it from bit. Hence, the idea that every physical quantity, every particle, every force, every element of space-time derives its existence from information. Bits, yes and no questions. Binary choices. Hence, the universe at its most fundamental level isn't made of matter. It isn't made of energy. It isn't made of space-time. It might be made of information. Hence, if this is true, and I think there's a reasonable chance it is, then the conservation of information isn't just a law of physics, it's the law of physics, the most fundamental principle there is. And it's more fundamental than conservation of energy, more fundamental than the speed of light, more fundamental than quantum mechanics itself. Information is the bedrock, and information is never destroyed. And what does this mean for us? What does it mean that the universe remembers everything? I think it means something both terrifying and beautiful. Terrifying because there is no forgetting. And every mistake, every cruelty, every moment of cowardice is permanently recorded in the quantum state of the universe. You can't hide from it. You can't erase it. It's there forever. But beautiful because every act of kindness, every moment of love, every flash of creativity, every instance of courage is equally permanent. Hence, the universe records the good and the bad with perfect impartiality. Nothing is lost, not the beautiful moments, not the terrible ones. All of it is preserved in the cosmic record. Hence, the people you've loved, the moments you've shared, the words you've spoken in kindness, all of it persists, all of it matters, not just in the human sense of mattering, but in the physical sense. Hence, your actions have permanently altered the quantum state of reality. They are woven into the fabric of the universe itself, and they cannot be unwoven. Hence, I've spent my career studying the most fundamental laws of nature. Black holes, string theory, quantum gravity, the fabric of space-time. And if there's one thing I've learned, one thing that 50 years of physics has taught me with absolute certainty, it's this. The universe wastes nothing, it loses nothing, it forgets nothing. And so every photon that was ever emitted is still traveling through space. Every quantum of energy is still somewhere in the system. Every piece of information is still encoded in the state of reality. And so we are the only part of the universe that knows this. We are the only ones who can look at the laws of physics and understand that the universe keeps a perfect record. And so we are the universe's way of knowing that it remembers, and that might be the most remarkable thing of all. Not that the universe remembers everything, but that it created something, us, that can understand that. It does. Thank you for listening. And remember, the next time you think something is gone, truly gone, erased from existence, physics says otherwise. The universe remembers, it always has, and it always will.